The Sakharov pump, or SRP, is a simple and reliable mechanism. However, when it comes to diagnosing and describing the physical processes in submersible equipment, things are far from simple. The classic method of determining the well state is plotting a dynagraph, a graph of the dependence of the load on the polished rod from its position. The raw data received from the sensors on the polished rod forms a surface card on which it is extremely difficult to figure out anything due to the vibration of the rod string. Therefore, using a mathematical model of the well, the surface dynagraph card can be transformed into a downhole card. By the shape of a downhole card, an experienced technologist can judge the condition of the well no worse than a doctor about the condition of the patient by his cardiogram. All malfunctions in one way or another affect the shape of the dynagraph, often overlapping and making the issue of diagnosis a task for experienced professionals. There is only one small problem. Even in a small oil field, a professional cannot monitor every well, and a malfunction not noticed in time can lead to expensive repairs and loss of production time. There is a logical desire to entrust diagnostics to the computer, but this task is unexpectedly difficult. What a human perceives intuitively is a non-trivial task for a computer. Therefore, for existing diagnostic algorithms, additional geometric constructions are performed on top of the dynagraph card. Now, it is nothing into it for the computer to determine the state of the pump. It is just to calculate the angle at which the tangent intersects the originate axis, and in this case, the mathematical model will show the filling of the pump. With other well conditions, similar actions are performed, building tangents, calculating angles, and intersection points with coordinate axes. In theory, it sounds simple, but there are a few pitfalls. Firstly, it's not easy to determine the points at which the tangent should be constructed. Do not forget that for a computer operating only with the coordinates of the dynagraph points, it is not empirically obvious where to draw a line. This problem can be tackled by fine-tuning for each individual well, but this is only a temporary measure because the wells sometimes change their behavior, especially when it comes to old oil fields that are on the verge of depletion. Secondly, some cards of classical malfunctions are just similar to each other. Computers can make millions of complicated calculations per second, but acting algorithmically, a pitiful machine cannot notice the difference between these cards or these, or these. It would seem that it remains to accept that the definition of emergency situations will remain the lot of experienced specialists, but this is only if you try to solve the problem head-on. In the past few years, pattern recognition systems have evolved rapidly, and today it's not difficult for computers to distinguish a cat from a dog in a photo, or even recognize a person by face. For such systems, special mathematical apparatuses, neural networks, are used. The neural network has a number of drawbacks. For example, it requires training, and the finished product is a black box. To look into it and understand how it works is extremely difficult. But that's a whole other story. The main thing is that a properly structured neural network, trained by an experienced technologist on several tens of thousands of dynagraph cards from real wells, is exactly what is needed for this task. Pattern recognition of malfunctions by shape of dynagraph make it possible to determine emergency and undesirable well conditions with high accuracy, even if malfunctions occur simultaneously and overlap each other on dynagraph card. And if we add classical algorithmic methods to the neural network in those places where they show the best side, the technologists will need only to wait for the alarm from controller to intervene and occasionally look at the list of oilfield wells without wasting time on questions that, in fact, do not require the attention of a valuable specialist. Well-sim pump-off controllers have implemented this concept of combining classical algorithms and pattern malfunction recognition, which in combination with SCADA allows to create a truly smart oil field, wherein even the overlap of malfunction patterns on one another is recognizable, which is not easy even for a specialist. Let's take a look at several cases of the well-sim controller neural network operation. Wear of pump valves is a very common malfunction. The operation of such a pump is still possible, but it's not worth delaying the repair. It is important to note that both valves often wear out simultaneously, and such a case is difficult to distinguish from liquid friction. The neural network in this case is guided by the characteristic radii of rounding of the corners of the dynagraph card. And here is an example of the overlap of two defects. Uniform rounding of the dynagraph shape indicates viscous friction, and the slope indicates non-anchored pipes. The classic case, the plunger's hit on the fluid, indicates insufficient filling of the pump and is the reason for increased wear and a hint for changing the well operating mode with a change in pumping speed or periodic accumulation idle time. The gas effect is a defect that is very similar in appearance to an hit on a liquid, but that is diametrically different in terms of elimination. The differences are minimal, a smooth line of falling load on the downstroke and a slight bend in the upper left. Also on this card the plunger hits at the top of the stroke. If the previous card were simply not optimal, then this one is already emergency and requires an immediate stop and urgent repair. Breaking of rods and gushing of the well, perhaps you can't imagine worse. But by four-handed stopping of the well, it is possible to reduce downtime by the time of the repair. The controller recognizes these and other patterns with an accuracy of 95 to 97% and also provides the user with the ability to use or recognize malfunctions as emergency set points that issue a warning to the dispatcher or stop the well. The use of advanced automation technologies requires time to get used to it, but the glance at the numbers of the increase in the overhaul interval from the correct operation of the wells is enough to understand that it is worth it.